Hi, my name is Matt.
Hi, my name is Prab. We are doing Hindmarsh Neuron model for E122 at San Jose State. This Hindmarsh Neuron model are based off these three equations, and it is used in robotics and other stuff to mimic real life movements.
So we took these differential equations and we were given a few initial conditions for the S, the R, and the RS, or the XR. And with these, we also took them into consideration of time scaling, which then helped make the whole process go faster. After we had solved the equations, we ended up with circuits that looked like these three. We have a combination of the X, Y, and Z output, which I'll then focus more on the circuit later. Currently, we have for input of a pulse wave set at 1 volt peak to peak, a frequency of 1 hertz, a width of 500 milliseconds, so half of it, and that's what we're using over here. So let's go to the circuits. Initially we have all of our initial inputs starting out with y, or minus y, minus xx, x cubed, z, and negative I. Now negative I in this case is coming from our function generator. What we see over here is in the middle, right in there, we'll see that this part with the capacitor right there is what does the integrating. So it takes all those inputs up in the upper left hand corner and it integrates them, and then over here we then take that output and then we invert it. So we have our x and then our minus x as our output. We then move on to the next part, which is our y part of it, and we have our inputs of x squared, y, and minus 1, and those then come in, get integrated over here with this capacitor. It's a little messy, sorry about that. And then that is our y output, and then we have our y output jump over and get passed through an inverting amplifier with a gain of 1, so that then we have our y and our minus y out here. Next, let's move on to the z part. Let's move this out of the way, where we have our inputs going from left to right of minus x, minus 1, and z. And then we have those come on down. They tie in over here, and you see this capacitor that makes it into an integrating amplifier. And then since Z does not need to be inverted, we just have our Z output right from here. We then one other thing that we also have is that we're making use, other than the LT 1058s, we're making use of some 8666. Now these are multipliers, and we're using them to take two inputs like a negative x and the x, and then we have the output over here of x squared, or minus x squared, and then we also take that minus x squared and then we use it with another multiplier with another minus x, so that we end up with x cubed, a positive x cubed. So all of those are what we end up with to have each one of these inputs over here. We use the capacitors over here to help filter out some noise from our voltage supply. Currently we have it set up to use, or to output, a minus 15, plus 15, which are used to power the op amps and the multipliers. And then we also have a positive 1. Now, nowhere in our circuit over here do we use a positive 1. What we do is we have it inverted to make a negative 1. We don't have it over here on our LT Spice simulation because we're able to then use any, we're able to make a negative 1 volt power supply. So let's get to the output. Here we have the output of the X signal. We currently see that it is doing its bursting mode and its non-bursting mode. This is during the input width. And this is at a current amplitude of 1 volt peak to peak. Now let's increase that up to 2 volts peak to peak, and we'll see that the width of the bursting part is increased. So you have a lot more pulses in there. Once we increase that up to 4 volts, we then see that finally the bursting takes up the full width of the impulse, the input from the impulse. And now let's also look at the Y output. We're switching from the X output to the Y output. Let's adjust for our scale here. So here we have the same thing with the Y. If we increase, we're initially at 1 volt peak to peak, we increase to 2 volts, you'll see that the bursting increases, and then we go to 4 volts where it's taking up the whole input. And finally, let's go over to the Z input. Let's hope it doesn't short out right now. And it does, so I'm going to need to restart this. Alright, sorry about that. So here we are back, and actually everything was okay, it's just that we were still at the 4 volts peak to peak. So here we have our Z output from the final inverting amplifier right there. And this is how it looks when it's scaled properly and not in its bursting mode. As we increase it to 2 volts, of course the scale gets bigger, so let's adjust that. And then when we increase to 4 volts, we see what we ended up with previously. So thank you for looking at our poster. It definitely was a fun and challenging lab.